Welcome you all to the week 8 problem solving session of Basic Calculus 1. Myself Guru Bhajan from Department of Mathematics, IIT Jodhpur. In this problem solving session, we do the illustration that are based on mainly application of derivative. Precisely, if I would say, we do the problems based on linearization and differentials and concavity of a function, and at last we conclude our session by doing some illustration over L'Hopital rule, which is a main application of derivatives. So let us start with the concavity questions. So in first question, let we have given a function minus 4ax cube plus 6a square x square, where a is a real number. Then we need to first determine the intervals of concavity in terms of a, and second one is find all the values of a for which the function has exactly one inflection point. So we have been given a function for which we have to find out the intervals of concavity that depends on in terms of a. So the parameter we are trying to find, we will try to find some interval of concavity that depends on the parameter or value of a. Next, we need to find out such values of a for which we have exactly one inflection point. So since we have include the parameter a here, so we let us mark it as subpart 1 and subpart 2 rather than a and b. So to find out the concavity factor, what we need to do, we need to first calculate the double derivative. So f dash x is 4x cube minus 12a x square plus 12a square x, because differentiation of x to the power n is nothing but nx n minus 1. Next is, when we do the double differentiation of it, we will get 12x square minus 24a. Seema, can you Miss Seema, can you mute yourself? Thank you. So this will be 24ax plus 12a square. So if you will take 12 common from here, you will get x square minus 2ax plus a square. If you will write like this is nothing but x minus a whole square. Now you know that for concavity, if we talk about concave up, our double derivative should be greater than 0, and for concave down, our double derivative should be less than 0. So from here, if you will observe that this f double dash is greater than equal to 0, because at a it can only 0, otherwise it will be greater than 0. So we can conclude that concave, F is concave up on whole R. Although one can say that it might be R minus A, because we talk about concave up, and concave up means double derivative should be greater than 0, strictly greater than 0. But here this only R is sufficient. The reason you will get soon why we are excluding A. Now for the next factor, we have to find out the inflection point. If you will observe here, F double dash A is 0, but concavity does not change near A. Therefore, therefore, there is only one possible candidate for an inflection point, that is this A, because otherwise the our function double derivative is strictly greater than 0. At except A, our double derivative is strictly greater than 0. Thus the inflection point candidate is only x equal to A. But since the concavity remains changed, you can say, if you will observe that there is a number line and there is a point A. So after this A, it is positive. Before this A is this double derivative is positive. At this A, this is 0. But concavity is remaining same. Before A, it is also concave up, and after A is also concave up. Thus, this x equal to A does not correspond to an inflection point. Then I'll let you know what is the inflection point and why we are not considering it as, because it's satisfying the double derivative equal to 0. Still, it is not an inflection point. We will discuss that. So there is no inflection point. So now we need to discuss 2 points. One is why we are considering x equal to A in concave up sense. Why we are not saying R minus A rather than R. So we need to do this comparison. Secondly, while finding the inflection point, we see for which value of x this f double dash derivative goes to 0 to judge the inflection points, because our double derivative is 0 at x equal to A. So definitely there is some ambiguity in our concepts. So let me clarify it. So first of all, let me mention a note. So no change in concavity. This is your, you can say, first. Therefore, no inflection point. So that means whenever we need to check the concavity, sorry, whenever we want to check the inflection point, our concavity must change near or around that point. Second one is why we include at x equal to A. At x equal to A, the curve just flatters momentarily. Flatter means you can say it is touching the x-axis, like you can say x to the power 4 kind of graph. So still its graph is concave up on whole arc. We do not say that it is not concave up at x equal to 0. So we include the whole real line. This is the answer of our first question, you can say. Now let us discuss node 2. Why we are still excluding a, because f double dash a is 0. So for that, the condition f double dash c equal to 0 is neither a necessary condition moreover to that nor a sufficient one. So natural question arises, what exactly this f double dash c equal to 0 give us? So the second point dedicated to that point that we are discussing, it is only a useful candidate condition. So that means it's just providing us a candidate that can be seen as, or that can be focus over that it can be an inflection point. How? So to discuss that, we shall first mention what is the exact definition of inflection point. We'll go step by step. First of all, we discuss the inflection point. Then we discuss why this condition is neither necessary nor sufficient, and what will be the exact thing by which we can judge the inflection points. So a point x equal to c is an inflection point if and only if the concavity changes sign around c. So definition just tells us that we only and only focus over the concavity changes near around c. If it is happening, then we say x equal to c is an inflection point. So now, what is the role of f double dash c equal to 0? So suppose if you put, or if you get some c for which this double derivative is 0. So this will provide you a suitable candidate only to check the concavity changes around that point or not. So next target should be sign change of f double dash. So this is your final necessary and sufficient condition, you can say. Necessary and sufficient condition. So what we have to do, we have to first put f double dash c0 to see what are the possibilities of the candidate. and I will also rectify it after some discussion. Then we have to see the sign change of this f double dash. If it is happening, then only we can guarantee about the existence of a inflection point. Otherwise we say inflection point does not exist, even our double derivative is 0 at that point. So next one is why it is not necessary or not sufficient. Obviously if it is not the case, because like that our double derivative is 0, still it is not an inflection point. So that means we need to give some counter examples for that. So first counter example is f double dash c is 0 is not sufficient condition. Why? So for this, if you will consider a function f(x) equal to x to the power 4. Now if you do the double derivative of this function, you will get 12x square. And you know that you can observe that f double dash 0 is nothing but 0. But while you even draw the graph of x to the power 4, it is like this. It is more over to this neighborhood of 0. It is more oriented or touching the x-axis. But in overall real line or overall plane, you can say this is nothing but a concave up function. Concave up in whole r, concave up on whole r. It is not changing the sign. Thus x equal to 0 will not be an inflection point. So but no sign change in concavity. Sign change means your f double dash derivative is after some c, you can say it is greater than 0. Before that c it is less than 0, changing the sign. Thus no inflection point. Now why it is not necessary also? So for that we have to see one another example. F double dash c is not necessary even. So to check this one, what we do, we consider fx to be x to the power 1 by 3. So f double dash derivative will be minus 2 by 9 x to the power 5 by 3. Okay, so if you will observe that here f double dash is not defined at x equal to 0. So here f double dash is undefined at x equal to 0. But sign of concavity changes near 0. Because if you will observe that this f double dash x is greater than 0 for all x from 0 to infinity, and this f double dash x is less than 0 for all x minus infinity to 0. So that means near 0 our function is changing the concavity sign. Therefore x equal to 0 is an inflection point. Hence from the above discussion we can write the correct or appropriate approach to find out the inflection point which is as follows. So first of all, we compute f double dash x. Second one is find the critical points via f double dash x equal to 0 and f double dash is undefined. Now the last task is we need to, obviously we are giving the possibility of two candidates. Either our double derivative should be 0, other side is from the above example our double derivative should be or maybe undefined at that point. Then at last we see the sign change in concavity. This is our necessary and sufficient condition, that our concavity sign must be changed near that point or near that best possible candidate, can say. So this is the best way to find out the, you can say, to find out the concavity, or sorry, to find out the inflection point. So now let us move to the next question, which is again related to the concavity. So for this one, consider the curve defined by x square plus xy y square equal to 3. So first part is find d2y over dx square. Next is determine where the curve is concave up or down. So if you'll observe that this is an implicit function, you cannot separate y as a function of x. Thus we need to do implicit differentiation. We need to find the double derivative in that sense. Then we discuss when the double derivative is greater than 0 or less than 0, that will decide the concavity up or down. So try this one. It is similar to the above concept. So try this one. So let us differentiate implicitly this function. This will be 2x, and here over xy we have to apply the product rule, that is x dy by dx, then y will be as it is, and differentiation of x is nothing but 1 plus y square will be 2y dy by dx. Since it's a dependent variable, so we have to apply the chain rule, and differentiation of constant is 0. Next, since we have to find out the double derivative, then we can again differentiate as it is the equation. So it will be 2 plus dy by dx plus x times d2y by dx square plus dy by dx plus, this will give you 2 dy by dx whole square plus 2y d2y by dx square to 0. From here we may substitute the value of dy by dx from, you can say, equation number 1. So let us find out explicitly what is the value of dy by dx. Or you may first of all separate dy by dx on left hand side, then you can also differentiate it again. I have done in this scenario. So I need to find out the value of dy by dx from here. So this will be minus y plus 2x divided by x plus y. So from here d2y. So it is obviously clear that differentiation of this, you can see, dy, we have to calculate dy by dx whole square also. So
Yes.
yes, Archit,
No, no, sir, nothing, sir.
okay. So from here d2y by dx square, it will be x plus 2y, which will be, you can see, minus 2 minus 2 times of dy by dx and minus 2 times of dy by dx square. So when you will substitute this value, you need to solve a little. So this will give you plus 2 times of y plus 2x divided by x plus 2y minus 2 times of y plus 2x divided by x plus y whole square. And when you will solve it, then at the end you will get the easiest expression, which is like this. You may check by yourself also. This will be like this. Okay, so this is about the first part. Now what about the second part? We need to see the concavity of our the function, you can say, of our y. Just a second please. So second part is, we need to see when our this double derivative is greater than 0, when this is less than 0. So if you will observe that this is kind of x cube. So whenever your x cube is positive, then this double derivative is negative. So if x plus 2y is greater than 0, then y is concave down.
Down.
When this x plus 2y is less than 0, then y is concave up.
Up.
Is it clear?
Yes, sir.
So on the similar note, we we are going to do one more question that is kind of related to inflection point, which is also again an application of, you can say, derivative and concavity. part of a concavity. So let we have given
Sir,
a yes.
sir, sir, in this question, can we find the inflection point?
You tell me, concavity is changing or not? Observe from second part. Our function is concave
Yes, sir.
down before this
Concavity is
line,
changing.
and after this line it is
Yes, sir.
concave up. So definitely concavity is
Yes, sir.
changing. So the whoever the point lying on this line are the inflection points, because before this line it is concave down, and after this line, or you can say reverse, it is changing the sign regarding this line. So whatever the points lies over this line are the inflection points for this curve. Okay.
Yes, sir.
So the next one is, we have given a piecewise function x cube when your x is less than 0. Another one curve is ax cube plus bx square when x is greater than 0. So first of all, find a and b such that f is twice differentiable at x equal to 0. Second one is, determine so I think we have done only two questions, so it will be question number 3, changing the numbering. So determine whether x equal to 0 is an, it has been direct asked whether this is an inflection point or not. So what is the meaning of twice differentiable? We know that for differentiability the continuity is the necessity condition. So first of all we need to maintain the continuity near around 0. So here your x is less than equal to 0. So we need to maintain the continuity at x equal to 0. We need to maintain the continuity of the first derivative at x equal to 0 to maintain our derivative at first derivative is continuous. Then we need to also maintain the second derivative. So you need to imply the three conditions for which you can find out the value of a and b. Then you need to find out the inflection point. So try this one. First part is easy. We have done a lot of questions in the previous tutorials when we are doing the concavity, oh sorry, when we are doing in the continuity. So try this one. What are the values of a and b?
Sir, A belongs to R and B equals to 0.
Good. So first of all, we need to make sure our function is continuous at x equal to 0. So for that, limit x tends to 0 minus fx must be same as limit x tends to 0 plus fx, which is same as f at 0. So if you will see here, limit x tends to 0 minus is nothing but f of 0, that is included here. So this is 0. Limit x tends to 0 plus fx is, it is a, obviously it is a polynomial, so this will also corresponds to 0. If you will put at 0 x at the place of x, if you will substitute 0 plus h, when h tends to 0, it will, you will get 0. Next, what about the derivative? So f dash x is kind of 3x square 3ax square plus 2bx. So again, we need to maintain the continuity here also, since we want to do the double differentiation. So from here again you will get limit x tends to 0 minus f dash x, limit x tends to 0 plus f dash x f dash 0. So obviously f dash 0 is 0, and from here you will get also 0 because it is a multiple of x, you can see, if you will take x common from here. But when you discuss the double derivative thing, then this will be 6x 6ax plus 2b. There will be a change, and what is that? When you will try to maintain the continuity at x equal to 0 here, so this will be like this. Since 0 is included in the first part of the function, so this will be 0, but the second part here will contribute now to b, because it is independent of x, so constant will remain the same, and this part will goes to 0 as x goes to 0 from the right hand side. So from here you will get b equal to 0, and a can be independent, and a can be any real number. It will not affect the twice differentiability of our given piecewise function. Next part is, we have been asked that for which value, or you can say x equal to 0 is an inflection point or not. So what is the answer for the inflection point? We need to check x equal to 0. What is the answer of inflection point? Let me
Sir,
repeat.
it is
Yes, say, go on, Archit. Archit,
it is inflection point if A is if A is negative.
negative. Okay,
No, sir. Sir, if A is negative, then it is not.
okay. So if you will observe from this double derivative, whenever x is less than equal to 0, you can see that our f double dash x is 6x. Since x is less than 0, obviously it is negative. But when you consider x greater than 0, our f double dash x is 6ax. To be a inflection point, x to be an inflection point, this a to be positive, so that there will be a change in the concavity sign. Thus, otherwise x equal to 0 will not be a is not be an inflection point, because our function concavity sign remains same. Thus, f x equal to 0 is an inflection point if a is greater than 0 only. So The last question related to this concavity part is as follows. This will you do by yourself. Just let me know what is your answer. So first part is find the intervals of concavity. The simple thing is that. Second, show that the function has two inflection points. So this question will cover both the things, concavity and inflection point, and even the concept of extrema in somewhat sense. Discuss how concavity relate with the behavior near extrema point. These three things you have to find out. So first you try at your own, then we will discuss it. So what are the intervals of concavity?
Sir, minus infinite to minus root 3 union 0 to root 3 concave down,
Hmm.
and minus root 3 to 0 union root 3 to infinite concave up.
Okay. So f dash x is minus 2x square divided by x square plus 1. So solve it a little. So this will be x1 minus x square divided by 1 plus x square whole square. Then this double derivative will be like this. So this will be minus, let's say, 4x divided by 1 plus x square cube. So what is the double derivative you are getting? 1 plus x square to the power 4. Here it will be as it is, that minus 2x with negative sign, 1 minus x square, 2 into 1 plus x square x. So when you solve this a little, in denominator you will get it as cube, and in numerator you will get minus 2x
2x
minus,
into x square minus 3.
sorry,
Sir, finally, I have got sir, 2x into x square minus 3 in numerator.
okay. So this is just a bit more calculation, which is like that only, minus 4x and plus 4x cube left only. So from here you will get 2x cube and plus minus 2x. So is there any calculation error?
No, sir, it is right. Just
It is
you
right.
have taken minus common.
So from here you will get 2x cube and okay, minus 6x you will get. Okay. So now we need to check the concavity up. So for concave up, what we do, we put this greater than 0. You may directly check when this sign is changing. First of all, see, will this denominator can ever be 0?
No, sir.
It is always greater than 1. Okay, so it will not affect in any manner the sign of this f double derivative. Now what is the effect can do? This x and this x square minus 3 factor. So if you will factorize this a little, you will get, let me write it here, 2x x minus under root 3 x plus under root 3 divided by x square plus 1 whole cube. So there is 1.0 minus under root 3 and plus
Plus
under root
root
3.
3.
If you will see any point after the under root 3, suppose 2, so this will be positive, 2 minus under root 3 will be positive, and 2 plus
Positive.
under root 3 will be positive. So this will be positive sign.
Positive.
When you will see any point between 0 and under root 3, suppose 1, so this will be positive, but this will be negative and this will be positive. So it will be negative. Now between minus under root 3 and 0, minus 1. So this will be negative, this will be negative, then it becomes positive, and this will be positive. Next, any point before minus under root 3, that is minus 2, negative, negative, negative. So again, negative. So now you need to choose for concave up only the positive sign, because our derivative should be, double derivative should be positive for
Negative.
concave up things.
Positive.
So
Negative.
f is concave up on, and we will choose only the open intervals, because we, excuse me, we talk about only the, we talk about only the you can say strictly inequality, strictly greater than 0. So on which interval it is positive? Minus under root 3 to 0 union under root 3 to infinity. Next, f is concave down on minus infinity to minus under root 3 union 0 to under root 3. Is it fine? So the
Yes, sir.
next part, we need to discuss that it has exactly two inflection points. Is it true it is only having two inflection point, or it is having three inflection point?
Sir, three inflection point.
Three inflection point. So there is ambiguity in the question. So it must have three inflection point. Why three inflection point? Because if you will observe that from here, one sign change, another sign change, another sign change. So it changing the sign three times. Therefore, and concavity, or sorry, inflection point only corresponds to those points where the function changes its concavity. So therefore, x equal to minus under root 3, 0, under root 3 are the inflection point. I hope I don't need to explain it again, because we have spent approximately 10 to 15 minutes of class over this inflection point concepts. These points majorly we are here seeing like that ki, our function should change the concavity around these points. So third part, discuss how concavity relates with the behavior near extrema. So what are the extreme points here? What is this f dash x? To check the extreme points, what we do? We put f dash x to be 0. So if you will observe that the only numerator will corresponds to 0, because the denominator is always well defined and is always greater than 1. So only the role play these 2 points x equal to plus minus 1 are the critical points. Critical points of f. Next, what is the value of f double dash derivative at 1? From here, where 1 is lying? In this interval. So f double dash 1 has negative sign, while f double dash at minus 1 is having positive sign. So this will imply that x equal to 1 corresponds to local maxima, and x equal to minus 1 corresponds to local minima. By which result I am guaranteeing this? Second derivative test for local extrema. So next is how it is relating with the concavity. So concavity changes help explaining curve, tending near extrema. Why? Because you are checking the sign of this plus a double derivative of sign of double derivative at 1 and minus 1, and this concavity sign convention telling you itself that this local extrema or this critical point is belongs to local maxima or local minima. Okay, so in this way this concavity is helping us to discuss the local extrema condition, or it is nothing but the second derivative test itself. So now we want to move over the questions that are depends on linearization and differentiability, or you can say differentials. So before moving to the linearization, let me formally recall what is the definition of linearization. So If f is differentiable at x equal to a, then the approximately approximating function Lx equal to f of a plus f dash of a x minus a. This, if you will observe that, you will get this by MVT, mean value theorem. So this is the linearization of f at a. Next thing is, if so our fx is approximated by this Lx, and this is called standard linear, because it's a linear function. If you will observe that there is only power 1, so standard linear approximation of f at a. Next is x equal to a is nothing but center of the approximation, because around a we are trying to find our approximation of f. So since we recalled this concept, now we can mention, or we can move to the illustration. Find the linearization of, the first one is, these are not that much difficult question. You just need to calculate the f dash at that point. For example, in this you have to calculate f dash at 1, then we have to substitute in the above linearization formula. So fx is under root x at x equal to 4. Third part is sin x, the trigonometric function at x equal to 0. And the last one is, these are the simple questions then that you can do by yourself. Most probably I would not be need to solve it here. You will let me know what are the possible answers for these subparts. So what are the linearization of the given functions?
Sir, for first one, sir, it's 2x minus 2.
Okay,
Second one, it's x plus 4 upon 4.
x plus 4 upon 4. Okay,
For the third one, it's x.
okay,
And sir, last one, minus 2 plus 2 root 3 into x plus pi by 3.
okay. So let me go through it quickly. What is the derivative of this one? 3x square minus 1, and f dash at 1 will be 2. So by the formula or by the linearization we know that, and moreover to that, f of 1 is 0. So f of 1 plus f dash at 1 into x minus 1. So this will be 0 plus 2 times of x minus 1, so which will be nothing but 2x minus 2. Second one is f dash x is, this was under root x, so this will be 1 by 2 under root x, and f dash at 4 is 1 by 4, and f at 4 is 2. So by the linearization this will be 2 plus 1 by 4 into x minus 4, which will give us x plus 4 by 4. Third one is f dash x sin x, the derivative of sin x is cos x. F dash 0 is 1, but f at 0 is 0. Thus by linearization we can say that this will be 0 plus 1 time of x minus 0, which is exactly the linear function x. And the last one, f dash x of secant x is secant x 10x, and f dash at minus pi by 3, this will be, so this will be 2 times of, is it correct? 2 times of, this will be negative quantity, so 10 minus pi by 3 is, I guess, 1 by under root 3, is it?
No, sir, minus root 3.
Minus root 3. And what about the first one, is it correct?
Yes, sir, f dash x will be sec x into 10x.
So f at minus pi by 3 is 2. So linearization technique will allow us to write it like this, into x plus pi
Sir,
by,
and sec x will be minus 2, so it will be plus 2 root 3.
second
Sir,
function,
sec at minus, yes, sir.
sec minus theta is always sec theta, similar to the cos function of minus theta is cos theta always.
Yes, sir, okay, okay, yes, yes.
2 minus 2 under root 3x plus, from here you will get 2 times of pi divided by under root 3. Is it correct? So this will be like
Yes,
this,
sir.
minus 2 under root 3 of x. Okay. So next is just a quick discussion or quick relation between the linearization of sum of two functions, how it relates to the individual linearization. So find the linearization of fx is equal to under root x plus 1 plus sin x at x equal to 0, and how this, how is it related with or related to individual linearization of under root x plus 1 and sin x. So you can clearly see that this fx is the sum of two functions. So we have been asked to find out the linearization of this you can say sum of the function this fx at x equal to 0. Then we have to discuss how this is related with the explicitly linearization of function of sin x and under root cos x plus 1 at x equal to 0 itself. So quickly you can do this and let me know the answer. What is the linearization of fx?
Sir, it is 1 plus 3 by 2x.
Okay, so f dash x is 1 by 2 under root x plus 1 plus cos of x. F dash at 0, 1 by 2 plus 1, which is 3 by 2. And while you talk about f of at 0, this is nothing but 1. So linearization of this f1x is nothing but 1 plus 3 by 2 x minus 0, which can be written as 3x plus 2 by 2. Now we have been asked to compare with the explicitly linearization. So I'm taking at gx and under root x plus 1. So g dash of x will be again 2 under root x plus 1. From here you can say that g dash 0 is 1, and from here you can say that gx is 1. So linearization of g, I'm denoting it with L1, will give you 1 plus 1 x minus 0, which is x plus 1. Next is some function hx, that is sin x. Now tell me the derivative of h dash x is cos x, and again h dash 0 is 1, and from here h of 0 is 0, and linearization of this hx is 1, oh sorry, 0 plus 1 into x minus 0. So what is the mistake? Okay, so here it is will be 1 by 2. So this will be 1 by 2. This is x by 2 plus 1, or which can be written as x plus 2 by 2. So from here, what will you get? So if you will check L1x plus L2x, so if you sum up it, this one plus x, this will give you 3x plus 2 divided by 2, which is nothing but Lx. So ultimately the linearization of the sum of the function is nothing but the linearization of them, explicitly addition of them. Okay, so next one is related to the differential. So let me recall what is the differential. If you have been given a function y equal to fx and this is a differentiable function, then dy is nothing but f dash x of dx. So question number 7, find dy of x cube minus 3 under root x 2. This is an explicit function I'm giving you, 2 by 3 xy minus x. Now quickly tell me the answers of these particular ones. So what are the answers?
3x square minus 3 upon 2 root x into dx. And for the second one, 3y power 1 by 3 into 1 minus y upon 4 plus 3x y power 1 by 3 into dx.
Okay, let's see. So f dash x in the first question, that is nothing but dy by dx, is 3x square minus 3 by 2 under root x, or we may write like directly like that only. So from here you can see that dy is minus 3 by under root x of dx. In the second part, if you will differentiate, this will be 4 by 3y to the power 1 by 3 dy. Let's say here, since we are treating y as a function of x, f dash of x plus x f dash of x plus fx minus, so fx means simply y minus 1 equal to 0. So from here we'll get dy to 1 minus y, and this will be 4 minus 3xy to the power 1 by 3, and in the denominator it will be 3y to the power 1 by 3. Is it like this, Ashit?
Is there a 4 plus or minus in the denominator?
4 plus. Thanks. So this is the simply differential, and the last one related to this one is as for each function fx, find, first thing is the change in f, that is delta f. Second one is df, that is differential. Third one is calculate their absolute error. Absolute error means you need to just calculate the mod of del f minus df. So what are the functions? The first function is fx equal to x cube plus 2x, and your point is 0, and your dx is 0.1, while in the second part your function is x minus 1 and the point is 0.5 and dx is 0.1. So let me just mention it here. What is the dx del f? This is nothing but x naught plus dx minus fx naught. Simply this is the change in f. And what is the differential? Recall that it is the derivative at x naught into dx, and when you will calculate these two you need to just subtract. So this is not that much difficult one. Quickly tell me the answers. So next we have to discuss the L'Hopital rule. So let us do it quickly. So what is f at x naught? It is f at 0, which is 0 cube plus 2 into 0, which will be 0. So f at x naught plus dx is f at point 1 is 0.1 cube plus 2 into 0.1. When we solve this we get 0.21. So the difference between this del left is f at 0.1 minus f at 0, which is exactly 0.21. Now the second one is the differentiation of this. We have to calculate f dash at x naught first of all. So f dash at x naught is f dash at 0, that means 3x square plus 2 at x equal to 0. So this will give you 2, and df is nothing but f dash 0 into dx, that is 2 into 0.1, it is 0.2. So the from here this is your a part, this is your b part, and c part is the absolute error. So absolute error will be del f minus df, which will be 0.21 minus 0.2, that is 0.01. So this is telling you that there is, if you approach with the differential one, and if you directly calculate the change in f, there is smallest error. There will be some error. Obviously the approaches are different, but you can approximate this one with the other approach, one with the other. In the second part, we need to do the same. Our given function fx is x minus 1, and our point is x is equal to 0.5, and our dx is 0.1. So f at 0.5 is 0.5, f at 0.5 plus 1 is 0.6 minus 1, that is minus 0.4. Now del f is f at 0.6 minus f at 0.5, that is minus 0.4 plus 0.5, that is 0.1. This one is our a part of second. What is the derivative of f? This is 1. So that means derivative of f at 0.5 is also 1. That means df will be f dash 0.5 into dx. That is 1 into dx is 0.1, that is 0.1. So is this the correct one, or we did some mistake? C part is del f minus df is equal to, although the question was x inverse, I mistakenly wrote x minus 1, so it got simple, and this will be 0.1 minus 0.1. Since it's a linear function, though, there will be a no difference of this, you can say, error. There is no error. If it is a non-linear function, then there definitely there will be some error, like the above one. This is a non-linear function, so there was a error, there was an error. So the last part of this application of derivative of today's class is L'Hopital rule. Although we have done it earlier, L'Hopital rule, in some questions, but there are different forms of L'Hopital rule to apply this one. So how? So we do it, evaluate of the following. So we do one by one. So first one is the basic one, limit x tends to 0 ln 1 plus x minus x plus x square by 2 divided by x cube. We need to calculate this limit. If you remember, L'Hopital rule only applied in two conditions. Either you have 0 by 0 form, or you have infinite or infinite form. And what is L'Hopital rule? That limit x tends to a fx by gx is same as f dash x by g dash x. Now in this scenario, check, this is 0 by 0 form or infinite by infinite form, or none of them?
0 by 0 form.
0 by 0 form, because ln 1 is 0, this is 0, this is 0, so numerator will be 0 and denominator will also be 0. So we apply the L'Hopital rule, so it will give you 1 by 1 plus x minus 1 plus x divided by 3x square. When you solve this a little, you will get limit x tends to 0 1 plus x square minus 1 divided by 3x square into x plus 1. So when you will solve this some more step, this will be 1 by 3 into x plus 1. Now is this any kind of indeterminate form?
No, sir.
So we can directly substitute x equal to 0. This is a continuous function, so this will give you 1 by 3. Is it clear? So now the next one is a different version of this L'Hopital rule, limit x tends to infinite x ln x divided by x square plus 1. So which kind of form is this?
Infinite by infinite.
So this is infinite by infinite form. So how we will do that? We can directly apply the L'Hopital rule here, because we know that L'Hopital rule applied to 0 by 0 form and infinite by infinite form. So we differentiate this one. So this will be ln x plus x into 1 by x, which will give you 1, and denominator is 2x. Now, is it an indeterminate form? Is it any kind of indeterminate form? So it is again an infinite by infinite form. We have to differentiate it again. So this will be limit x tends to infinity 1 by 2x. Now this is not any kind of indeterminate form, so we may directly substitute. In the next part, we will not get directly the indeterminate form. We need to make it, or we need to neutralize it to the level of when we apply, when we may apply the L'Hopital rule. Which kind of form is this? First of all, why we are considering this zero positive? Tell me.
So because log is defined only for positive real number.
Good one. So what is kind of form is this? 0 into
Infinite.
infinite form. So obviously you cannot apply L'Hopital rule here directly. Okay. So what will you do? You will rewrite it in this sense that ln x divided by 1 by x. Now what is the form? Is it infinite by infinite form?
Yes, sir.
So now differentiate this one. This will be 1 by x, this will be minus 1 by x square. So this will give you limit x tends to 0 positive of minus x. So this will give you 0. Now let us discuss one more indeterminate form that is also not exactly applicable, where exactly L'Hopital rule you cannot apply. You will get to know why we are considering it here 0 positive. So which kind of form is this one?
0 power infinite.
No. Check check it again.
So 1 power infinite.
1 to the power infinity form. Observe here. Here you cannot say this is exactly 1. Why? Because it is tending to 1 and you are moving from the positive side of x. So it obviously can be a little greater than 1. Whenever you put any power of 1, it will be 1 itself. But what about 1.001? Will it be 1 remain?
No, sir.
No. So that is why this is kind of a indeterminate form. So therefore what we will do here, we will first of all let this limit is equal to L, so that we can make this expression into the 0 by 0 form, or you can say infinite by infinite form. So what we can do here, we can apply ln of L on both sides. Now tell me, ln is a continuous function.
Yes, sir.
So can we take out the limit outside?
Yes, sir.
Recall that limit of x tends to c, we learned from one problem solving session, is nothing but f of limit of x tends to c of x, that is f of c, right? So this is the same step. We are just doing like this. Clear? So ln x to the power n is, any doubt, Archit?
No, sir.
So this will give you ln 1 plus x divided by x. Now tell me what is the form of this expression? This is
0 by 0.
0 by 0 form. So we can apply the L'Hopital rule here. So what is the L'Hopital rule will give us? 1 by 1 plus x divided by 1, which is nothing but 1. But this is the value of ln L. But you have to find out the value of L.
Mm.
ln L equal to 1. So LV will be equal to e to the power 1. That is E. So this is the standard famous property of this limit that we usually cram it, but you can directly find out with the help of this L'Hopital rule. You don't need to go with this one, or you don't need to remember it. So this is E, and the same way if you will move with 1 by 1 plus x to the power x, 1 to the power infinity, again the same form. So the last part and the last question is limit x tend,
Sir,
just a
sir,
second,
sir.
let me write, let
Yes,
me
sir. Yes, yes, sir. Yes.
1 by ln x. Let me mention one point here. We have taken 0 positive. The reason is your ln function should be well defined over there. Yes, now you can ask.
Sir, I thought that any number greater than 1 power infinite will be infinite. That is not correct.
Yeah, that will be infinite, but this is approaching, this is indeterminate form. You cannot guarantee that how much you are adding to 1, since x tending to 0 positive now, so it is approaching to 0, and your this internal expression is approaching to 1. So you cannot guarantee, suppose 1.011, there will be some quantity near around 1, there will be some quantity 1.1 whose power infinity is something more than that. So in the same way, this is kind of an indeterminate form that you cannot tell the exactly what will be the value. So that is why we are following this method, so that our conclusion is its value is E. It is not infinite. This is the clear proof of that you were thinking about. This is not infinite. This is what the value of E. Okay.
Yes, sir.
So this is the last one. You try this one. This is a mixed kind of obviously mixed kind of this rule indeterminate form. So you need to follow up with the previous one, previous subpart, that you have to assume that it is equal to L, then you have to take the log on both sides, then you have to calculate its limit. Quickly tell me the answer. Uchit, where were you in the last session? I think you were not present now.
Yes, sir, sir. Sir, actually, sir, there is a wedding I have to attend.
Okay. So I hope you have followed up with the previous lecture or notes and lecture video.
Sir, I have not got the time. Today, I am back to my routine, sir. I will follow that.
First go through it, then you may ask in the next class any doubts regarding that.
Okay, sir.
So did you got any get any answer? This is kind of, you can say, mixed form. So we'll try to approach like this: ln sine x the power 1 by ln x. So this will be ln sine x divided by ln x. Which kind of form now it is looking like?
Infinite upon infinite.
So this will be limit x tending to 0 positive 1 by sine x into cos x by chain rule. This will be 1 by x. So from here this will be limit x tending to 0 positive x by 10x. What is again 0 by 0 form?
Yes, sir.
Since we are doing that, so we will follow that, directly putting it equal to 1 rather than 1 by, what is the differentiation of 10x?
Sec square x.
So this will be 1 by 1. So that means the value of ln L is 1. So L will be,
E.
okay.
Yes, sir.
So if you will see that this is nothing but the 0, ln 0 is
Not defined.
0 plus. So it's going to minus infinity. So 1 by ln x will be go to 0 by 0 to the power 0 form kind of.
Yes, sir.
So this is all about today's class. If you have any query, you can ask. So if not, so let's end this session here. Let's meet on next Tuesday.